All right, let's dive into the invisible forces that are quite literally powering our world. We're going to trace a path from some fundamental ideas in electrostatics all the way to the tech in your pocket. And it all kicks off with one pretty wild question. So think about this for a second. That little flash on your camera, how in the world can it be brighter than the actual sun, even if it's just for a fraction of a second? I mean, where does that insane, instantaneous burst of energy even come from? Well, the secret isn't about having a tiny power plant in your camera. No, it's way cleverer than that. It's all about the ability to slowly gather up electrical energy, store it, and then unleash it all in one massive, powerful punch. That's the story we're going to unpack today. Our journey begins with a really elegant tool for understanding the invisible electric world around us, Gauss's law. And don't worry, we're not going to get lost in complex equations. This is all about the big, brilliant idea behind it, a kind of cheat code for physics. So, what is this law really? Put simply, it says that if you want to know how much electric charge is inside a closed-off area, you just have to measure the total electric flow coming out of it. Think of it like this. Imagine you need to count how many people are in a building, but you can't go inside. Well, you could just monitor all the doors. If you count how many people come out, you'll know how many were in there to begin with. Gauss's law does that, but for electric charge. It's a fantastic shortcut. And using it is like a simple 3-step recipe. First, you just imagine a nice symmetrical bubble around whatever charge you're looking at. Second, you figure out the total electric flow that's poking through that bubble's surface. And bam, step 3, that number tells you exactly how much charge is trapped inside. It's just a beautiful, logical process. Now, this simple law leads to some really mind-bending results. Here's a big one. If you take a hollow metal ball and spread electric charge evenly all over its surface, the electric field inside that ball is 0. Absolutely nothing. It's totally shielded from its own charge on the outside.
And this isn't just some physics trivia. This is a huge deal. It's the principle behind electrostatic shielding. It's why your sensitive computer parts are inside a metal case, and it's exactly why you're safe inside your car during a thunderstorm. The car's metal frame acts like a Faraday cage, forcing that massive electric field from the lightning to stay on the outside.
Okay, so we've used Gauss's law to get a sense of the forces at play. Now let's build on that and create an energy map of this world. And for that, we need to talk about potential. You've definitely heard of electric potential before. We just call it voltage. The best way to think about it is like a topographical map for energy. You know how a map shows you the height of hills and mountains? Well, potential shows you the energy height at any point in an electric field. It tells you how much work you'd have to do to lug a charge up to that spot. So let's nail down this difference. The electric field is like the steepness of the hill. It's all about the force that's pushing or pulling on a charge. But the potential, that's like the height of the hill. It's about the stored energy a charge has just by being at that location. One's about the push, the other is about the position. So we have this energy map. What do we do with it? Well, this is where we get to the real hardware. This brings us to capacitors, the devices that are literally built to harvest and store that energy from the field. At its very heart, a capacitor is basically a bucket built for holding electric charge. Or think of it like a tiny, tiny battery that can charge up and, more importantly, discharge incredibly fast. So how do you make a good charge bucket? The principle is just ingenious. You start with one charged metal plate. It can hold some charge, but not a ton. Now watch this. You bring a second grounded plate really close to it. The presence of that second plate makes the potential, or the energy height, of the first plate plummet. And because of the simple relationship C equals Q over V, if you lower the V, you can pile on way more charge Q. You've just massively increased its storage capacity. Okay, great. We can store energy. But you know how it is with technology. We always want more. More power, smaller size, better efficiency. So, how can we level this thing up? How do we make our capacitor even more powerful? Well, the answer is to stick a special ingredient in between those two plates. This ingredient is called a dielectric, and it pretty much acts like a supercharger for our capacitor. Now, a dielectric is actually an insulator. We're talking about stuff like glass, rubber, or plastic. But it has this one really neat trick up its sleeve. When you put it in an electric field, its molecules don't move, but they stretch and align themselves with the field. The material becomes what we call polarized. Let's zoom in on this. See how the molecules start out all jumbled and random,
But as soon as we apply that external electric field, bam, they all snap into alignment. And here's the kicker. By doing that, they create their own tiny electric field inside the material that actually pushes back. It opposes the main field. And here's where the magic happens. And it's a little counterintuitive. By sticking this insulator in there, you make the capacitor stronger. Because that little pushback from the dielectric weakens the overall field, it lets you cram way more charge onto the plates at the exact same voltage. The capacitance just goes through the roof. Now, real quick, in actual circuits, you often have to combine capacitors. The rules of thumb are pretty simple. If you link them up in parallel, they're sharing the charge, and you just add up their values to get a much bigger total capacitance. But if you link them in series, they're sharing the voltage, and the total capacitance actually goes down. So let's just recap the whole journey. We started with Gauss's law to map the invisible electric field. Then, we used electric potential to turn that map into an energy landscape. From there, we figured out that capacitors are the devices built to actually store the energy from that landscape. And finally, we saw how dielectrics act as a supercharger, letting them store even more. And just like that, in a few minutes, we've traveled from these fundamental, kind of abstract laws of physics, right to the core components that make all of our digital lives possible. These concepts aren't just in a textbook. They are the literal building blocks of technology.
And that brings us right back to that camera flash. But it's also the tech in a defibrillator that saves a life, and it's at the heart of your computer's memory. All of it relies on these exact principles. So, I guess the question to leave you with is, as we get better and better at this, what will the next leap in energy storage make possible? What's coming next?